Welcome back. In this module, we're going to talk about weighted least squares and robust regression. So let's talk about second-level analysis with robust regression. What robust regression algorithms are a class of algorithms that are designed to be less influenced by extreme values. So this is a potential way to deal with outliers and extreme observations in your design. High variance observations, which are far out from their respective means or regression lines on average, tend to dominate the results if those observed values are extreme, especially. So what we're doing with any kind of least squares estimation is minimizing least squares. So what that means is that outliers, things that are far from the regression line, have more pull. Also, if those values are extreme on the predictors, they have high values on the x variables or predictor variables, they have high leverage, and they can be very dangerous because they're going to exert a tremendous pull on the regression line. So this creates a lot of problems for the standard analysis framework. When you can't check the assumptions at each voxel and check for the normality of the distribution and the presence of outliers, then automatic procedures for weighting the observations based on their potential outlier status are advantageous. And that's what robust regression is all about. So let's look at an example. Here's some null hypothesis data on the left with 50 subjects. So as you can see, there's no effect here in this sample. And now we have the same exact data, but we've included one outlier point, which is high out on the x value, on the x-axis. So it's got high leverage, and it's high variance, so it's going to tend to be really have a large value on the y-axis in one direction or the other. And as you can see, this one data point now produces a significant result in our regression. That's a problem. So the structural model for the general linear model, to review, is y equals x times beta plus error in matrix form. And now let's consider that we want to weight some observations more than others. So let's come up with a vector w, which has weights for every observation. Let's define a matrix Q then, which is a diagonal matrix that applies those weights when you multiply it by a series of data, by a data vector. So there's Q with the weights in the diagonal. And now we're just going to multiply each part of that structural model equation by Q. So Q times y equals Q times x times beta plus Q times error. Now, let's also define a matrix W that's Q transpose times Q. So in that case, the solution to the beta is, the beta hat, that's the estimates of beta, is x transpose Wx inverse, x transpose Wy. So that weighting matrix W applies the weights, and now I'm estimating the betas in a way that, that includes the weights on the observations. So that's the basic principle behind weighted least squares. And beta hat is the weighted least square solution for the data. So weights can be used, and this framework can be used in a number of different ways. So this is really fundamental. So these weights can be used to adjust for inequality of variances, heteroscedasticity. So if the weights, for example, are inversely proportional to the variance of a group. Secondly, it can be used to decorrelate or whiten autocorrelated data. If you can estimate what the form of autocorrelation is, serial autocorrelation, and then use weights that are proportional to its inverse. Third, it can correct for non-independence in repeated measures designs. So if you're sampling the same observations for time 1, time 2, time 3, there's some correlated structure, and that can be estimated and controlled for in this way. And finally, the subject of today's lecture, it can be used to downweight extreme values or potential outliers in robust regression. And by the way, in all these cases, the betas, the variance estimates, and the degrees of freedom have to be adjusted as well for the fact that you're weighting the observations. So here is robust regression algorithm with iterative generalized least squares. And we'll just walk through how the algorithm works in its basic form. So first, we often weight based on the inverse of the leverages, so we don't want extreme values to dominate even our initial fit. We fit the weighted least squares model, and then we scale the residuals by a robust estimator of their outlier status, how far they are from the regression line. And we apply a weighting function, and that you can see in C. There, down at the bottom, you can see a couple of popular robust weighting functions, the bi-square function or a Huber function. Once we do that, we refit the model in weighted least squares with the extreme values downweighted, and we iterate those steps until the algorithm converges on a solution. And then finally, once we've converged on a solution, we adjust the variances and degrees of freedom so that we can get valid and accurate p-values. So now let's look at our null hypothesis data case. There's the original data, there's the data with an outlier with a significant positive slope. When we fit robust regression, this is the IRLS solution to that. And what you can see here is that the weights, the darkness of the point is proportional to the weight. And here this extreme value is a clear white circle. So that means that its weight in the final model is basically 0. Most of the other points have solid black circles indicating that they have high and equal weights. So effectively what we've done here is we've downweighted that one extreme value, and now we get something that's again closer to the right solution. So now let's look at a case study from some actual fMRI data. And we'll look in the right motor cortex, and we're going to look at a series of conditions where people made button press responses with the left hand or the right hand. So what we see here is t-scores from a group analysis in 8 conditions. The first 4 conditions are button presses with the right hand, so we shouldn't see a strong response. And the last 4 conditions are button presses with the left hand, so we should see a substantial right motor cortex response. And now what you see is in the black lines here, ordinary least square solutions, and indeed the t-scores are substantially higher for the left button presses than the right, so that's good. Now let's look at the robust solutions, which are in gray, and the t-values, especially for some of those conditions, are quite a bit stronger for conditions 5 and 6 there. And these actually happen to be the conditions where there are extreme values in one subject that go in the opposite direction. And finally, the univariate case refers to the idea of trimming the data or just removing outliers that are extreme values without the robust weighting procedure. And as you can see here, there's really no benefit here to the univariate outlier removal. And this has been a pretty consistent finding that the univariate outlier removal is not a terrific solution, and robust regression is a better one. So here, the conclusion is increased power with robust regression, and there's really little or no cost here that's apparent. Let's look at another case study from another study. This is a study where there's both visual responses and there's also painful events. So what we expect to see is activity in the visual cortex for visual responses and activity in the somatosensory cortex, especially S2 in the posterior insula, among other regions, for pain. On the first column here, you see the OLS solution for both, and you can see visual activity. It's unilateral, left side only for the OLS in vision. The middle column is the IRLS solution, and as you can see here, there's bilateral visual activity, and there's also responses in the pain areas that we expect. And now the final column on the right shows you the map of where there's significant differences between them. So what you can see here is stronger statistic values in the visual cortex for visual responses and in the posterior insula and S2 for pain, which is exactly where we expect to see real results. So here, there are higher t-scores with robust regression in areas in which we expect true effects. So that's good news for robust regression as well. Now we'll look at some simulations. So what you see here is a series of simulations where there's no outliers in the data. So all the assumptions actually hold. So we shouldn't see a benefit from robust regression here, but we can evaluate the costs. And on the top panel, there's no true signal, and we can look at the false positive rate. The x-axis is the sample size, ranging from 5 up to 40 subjects. And what you see here, and the bottom panel shows you power when there is a true effect, which increases with the sample size. So let's look at the power curve first. The IRLS solution has with no outliers, has a very small cost in power. The line is below the other lines, but there's a very small cost. And what we're comparing it to here is, in blue, the ordinary least squares solution. In the light blue line, univariate outlier dropping. The green line, multivariate outlier removal with Mahalanobis distance. The red line and black line are both robust regression, IRLS algorithms with different weighting functions, the bi-square and the Huber weighting functions. So what we see is a very small cost in power, but not really much of a problem. And now when we look at false positive rates, we can see that it appropriately controls the false positive rate. In fact, the only algorithm that doesn't control the false positive rate, where the actual false positive rate is higher than the nominal one, is the Mahalanobis distance-based outlier removal. And this is a cautionary tale that, that trimming and removing outliers can sometimes have unexpected effects unless we really know how it's behaving in the data. So we should do those things with caution. So there's the increase in false positive rate. So now we'll look at a case, and these are brain behavior correlations where we have multivariate outliers, values that have higher variance on both the predictor and the outcome. And what do we see here? Well, with multivariate outliers, all of the methods show increases in false positive rates above the nominal false positive rate of 0.05, which is the solid horizontal line. But the worst of those is the ordinary least squares solution. And the IRLS solutions are actually better than ordinary least squares in terms of false positive rates. Now here, the Mahalanobis distance, the multivariate outlier removal, is performing better, but that's really because the procedure that was used to remove outliers was exactly the procedure that's used to generate the outliers. So in that case, it can be a win, but on average, the multivariate outlier removal isn't a good idea unless you really know that it's performing well and is valid for your data. So IRLS here is better. And then finally on the bottom, we're seeing the case where there really are true effects, but there are also outliers. And the IRLS is the most powerful. Here it's the bi-square weighting function when true effects are present. And ordinary least squares is the worst. So ordinary least squares is not very robust to outliers in terms of power. And finally, univariate outlier removal here is again suboptimal. It's performing really not much better at all than ordinary least squares. So robust regression can help, and it can help even with very large data sets. So this is some recent work by Virgil Fritsch et al., and it's from a European imaging genetic study with 1,500 people. So you'd think huge sample size, right? What do we need to worry about these few outliers for? A few bad apples. Well, what they're showing here in this map is it's an anger recognition task, and they're showing greater reproducibility of the maps in other ways I'm not showing you here, and more putative true effects detected during anger recognition. Here there's stronger effects in the striatum and some additional things that show up with the robust linear model, that's the bottom series, versus OLS on the top. And interestingly enough, they also have cases where they believe that they found false positives that go away with robust regression. So what you see here on the left is a blob in the thalamus that's a significant result under ordinary least squares and not under the linear model. And when they look at what's happening in the thalamus, what you see there is, and this is a correlation between impulsivity and brain scores, and then they plot that correlation, you can see that there's extreme heteroscedasticity, there's inequality of variance, and there's a few points, there's a skew in the impulsivity score, so that there's a heavy tail on the right end. And that means those points have a lot of leverage. And as you can see, there's one point there on the bottom right around impulsivity score of a little higher than 8 that out of 1,500 subjects has this very extreme value, and they have a very extreme brain value as well. And that subject was enough almost by themselves to drive a significant group result. So the IRLS procedure, robust linear model, downweighted this extreme value. So it's a clear circle, not filled, so its weight's very low, and the significant result goes away. So this is an example of how even in large samples we can end up with fewer false positives in some cases with robust regression. So let's summarize. Ordinary least squares models are influenced by outliers, like all models. T-tests are fairly robust against false positives, but they're really not robust against loss of power. And this is even more true with regression and correlation. So regressions and correlations are not robust against loss of power or false positives, so we can end up with lots of problems. Robust regression is a good way to minimize the influence of those outliers, especially when you can't check the assumptions and data at every test performed. So there's a small cost in power when the assumptions hold, but potentially larger benefits when there are some problems with the data. And here's some further reading on some of the older and recent papers on robust regression in neuroimaging. And finally, thank you for your attention.